the first part of this module 14, we talk about the rate of a reaction. In this second part, we're going to talk about some factors that affect the rate of reaction. And also we're going to talk how the rate could help us to determine a mechanism that explains the reaction. By the end of this model, you will be able to explain how the activation energy affects a rate and be able to use the Arrhenius equation. Also, you will predict the rate law for a reaction having a multi-step mechanism given the individual steps in the mechanism. And finally, you will explain the principle underlying the catalysis. We saw in the previous model the first and second order reaction, but also we can find some zero order reaction. This is independent of concentration of the reactant. The rate is equal to the constant rate. For a zero order reaction, the rate is equal to the constant rate and basically is independent of the reaction. So it's a linear with respect to the concentration, but the rate doesn't depend on concentration. So it just depends on the constant rate for the zero order reactions. So let's go and talk a little bit about some factors that affect the reaction rate. First, the temperature. Another factor is the frequency of collisions. Also, the orientation of molecules. And finally, the energy needed for the reaction to take place, and this is known as the activation energy. So let's talk a little bit about the effect of the temperature and the rate. Generally, as the temperature increases, the rate also increases. The rate constant is temperature dependent. It increases as the temperature increases. Here we have a graph of methyl isonitrile, the reaction of methyl isonitrile to produce acetonitrile. And here we can see that as we increase the temperature, the rate of the reaction also increases. Okay, so here we see the effect of the temperature on the constant rate. Okay, so as the temperature increases, the constant rate also will increase. So the rate constant doubles with every 10 degrees of increase of the temperature. The second factor was or is the frequency of collisions. The collision model is based on the kinetic molecular theory. Molecule must collide to react. If there are more collisions, more reaction can occur, okay? But it's important to understand that not all of them that collide they're going to react, okay? But if you have more collision, the probability to have a reaction is going to increase also. So if there are more molecules, the reaction rate is faster. Also, if the temperature is higher, molecules move faster, causing more collisions and a higher rate of reaction. So the point is that we need more collisions. So you can increase, you can increase the more collision by increasing the number of molecules, because if you have more molecules, the probability to collide with another one is pretty high. And also, if you increase the temperature, that will give a lot of kinetic energy to the molecules. They will be moving faster, and that will cause more collision between the molecules. The third one is the orientation of the collision. This is really important. In a chemical reaction, bonds are broken and new bonds are formed. Molecules can only react if they collide with each other. The orientation of molecules. Molecules can often collide without forming products. Aligning molecules properly can lead to the chemical reactions. So bonds must be broken and made, and atoms need to be in proper position. So the orientation is really, really important. It's not just only that you collide two molecules and voila, you have a product. No, you need to have those molecules in the proper orientation. Okay, they need to be aligned in the right way. So, for example, here we have an atom of chlorine, and this molecule is chlorine, nitrogen, and oxygen. So, when this chlorine collide with this other chlorine of the molecule, that will produce a CO2, the formation of CO2 and the nitric oxide. But in the lower one, we can see that the chlorine is not colliding with the other chlorine. So that's why even though you have a collision, you don't have the product that you desire because you need to be in the proper alignment of the molecules so you can have the uh, the formation of the product. So the orientation is important. And finally, the energy needed for a reaction to take place, that is called as the activation energy. The minimum energy needed for a reaction to take place is called the activation energy. An energy barrier must be overcome for a reaction to take place, much like the ball must be hit to overcome the barrier in the figure below. So, if you're playing golf and you have this barrier, you need to hit the ball so that ball with enough energy that could overcome that barrier and then go to this side to make the hole. So, in the reaction, we have the same concept. Okay, in reaction, we need to have that minimum energy so that reactant can collide in the right position and make the products. Now, the reactants gain energy as the reaction proceeds until the particles reach the maximum energy state. The organization of the atoms at this highest energy state is called the transition state. So when you reach that higher point, that is the energy required, that you need to overcome to have your product. At that point, you have um, a complex of the reactants, and that complex is called the transition state. The energy needed to form this state is called the activation energy. So let's see an example. And in reaction progress, we have plots that made to show the energy possessed by the particle as a reaction proceeds. So here we have reaction progress. The reaction progress is basically in the x-axis is the time, and the y-axis is potential energy. So here energy versus time. Here we have our reactant that in this case is the methyl isonitrile, and as time progresses, this molecule gain energy, okay, and reach the top, the highest point of this reaction. This is the highest point that has the higher energy, and at this point, this molecule has this transition state. It has this rearrange in the structure, and is a really unstable um, state. Okay, so once you are here, now you are in the top, and you have overcome the barrier, and then you can go down to produce the product. Okay, so here you have the reactants. The reactants need this to gain this energy so it can form the products that you expected. Now you can see that there is a difference in energy between the reactants and the products. As the highest energy state, the transition state is formed. Reactions can be endothermic or exothermic after this. In this case, the products that are this one, the acetonitrile, has a lower energy than the reactant. So that means that the energy was released. So because of that, this type of reaction is an exothermic reaction because the product has a lower energy than the reactant. Okay, if the product has a higher energy than the reactant, then that reaction is an endothermic one. The relationship between activation energy and temperature. Arrhenius noted the relationship between the activation energy and the temperature, and he established this equation. K is equal to A E minus EA over RT, where K is the rate constant, EA is the activation energy, R is the gas constant, and T is the absolute temperature. Now, this variable, the A, is called the frequency factor, and this is a constant. This factor is related to the frequency of collisions and the probability that the collisions are favorably oriented for reaction. Now, if we apply the natural logarithm to this equation, we're going to find something like this. The natural logarithm of k is equal to minus EA over RT plus natural logarithm of A. And this is basically equal to the line equation once again. So if we plot this equation, natural logarithm of k is y, at t, 1 over t is x, and the natural logarithm of a is the intercept. So the slope is minus ea over r. So from the slope of this figure, of this graphic, we can obtain the activation energy. But remember, once we have the slope, we need to multiply by the gas constant, because the slope is equal to the activation energy over the gas constant. Okay, so if we determine the slope, we multiply by r, and that will be basically the activation energy for the reaction. Also, we can combine, because the constant rate is dependent on temperature. We can have also this type of reaction where we can obtain two different constant rate at two different temperature to obtain the activation energy for that reaction. Okay, so this way, if we have two different temperatures, for each temperature, remember that the rate constant is dependent on temperature. So that's why we need to use this type of equation if we have two different temperature and we want to determine the activation energy. Now that we have a little bit more knowledge about chemical kinetic, it is important to understand that kinetics gives what happens. We call the description the rate law. So with the kinetics, we know what happens. But why do we observe that in the rate law? We explain with a theory that's called mechanism. A mechanism is a series of stepwise reactions that show how reactants become products. So with the kinetics, we understand what happens, but with the mechanism, we understand how that happens. So reaction mechanism. Reactions may occur all at once or through several discrete steps. Each of these processes is known as an elementary reaction or elementary process. So each step of the whole process is called elementary reaction or elementary process. These elementary processes can have different numbers of reactants, and this is called the molecularity. The molecularity is of an elementary reaction tell us how many molecules are involved in that step of the mechanism. So if in one step we just have one molecule, it is called an unimolecular um, elementary step. And this is just one reactant for that specific step, okay? And each of those elementary step has also the rate law. So for, in this case, for a unimolecular reaction, a step or um, elementary step, we have the rate is equal to K times the concentration of A, just one of the reactant. We can have also an elementary step with two molecules, a bimolecular elementary step. Those molecules could be the same or different. The important thing is that you need to have just two in the reactants, okay? So the rate law is going to be Ka square in this case because both of them are the same molecule, or also the rate is going to be K times A concentration of A concentration times the concentration of B. That's when we have two different reactants. And the third example is called the thermomolecular, when we have three molecules in the reactant for each um, um, elementary step. So in this case, we have the three molecules are the same, so that's why we have the rate expressed by K times A cubic. If we have two that are the same and one is different, well, we just put the ones that is two with a square and the other one as a first order reactant. And if we have three different, that will be the rate will be expressed by the rate constant times the concentration of each of them. Thermomolecular. The thermomolecular steps require three molecules to simultaneously collide with the proper orientation and the proper energy. This type of elementary steps are rare, if they indeed do occur. This must be slower than unimolecular or bimolecular steps. Nearly all mechanisms use only unimolecular or bimolecular reaction. So it's interesting that if we have maybe different numbers of elementary step, the probability that one of those is going to be slower than the others is high. So what limits the rate? The overall reaction cannot occur faster than the slowest reaction in the mechanism. We call that the rate determining step. So one of those molecular or elementary step is going to be slower than the other one, and that one is called the rate determining step. So here we have, for example, in A, we have car slow at toll plaza A. So the rate determining step is the passage through A. In the second example, we have car slowed here at toll plaza B. So the rate determining step is passage through B. So here is basically the same concept with the elementary step. One of them is going to be slower than the other one. So that one is called the rate determining step. What is required of a plausible mechanism? First, the rate law must be able to be devised from the rate determining step. Okay, so because that elementary step is the one that is the slower one, that is going to dictate which one is the rate law. The stoichiometry must be obtained when all steps are added up. Each step must balance like any equation. All intermediates are made and used up, and catalyst is used and regenerated. As I mentioned before, the mechanism, remember the mechanism is a group of elementary steps. Okay, like so they are like small reactions that all combine. It's known as the mechanism that is created to try to explain how do you obtain your products. Okay, so let's see the following example. We have this overall equation: NO2 plus CO producing NO plus CO2. Okay, and the rate law for this reaction is the following. The rate is equal to the rate constant time the concentration of NO2 square. So let's take a few minutes to explain and highlight some things here. This is the overall reaction. These are the reactants, these are the products. Remember that in the rate law, we express the rate law as the concentrations of the reactants that affect the rate. So here we can see that we have a reaction where we have two different compounds, two different reactants, and just one of them is part of the rate law. Okay, so that means that the CO, it has an order of 0 in this reaction. Okay, it doesn't matter how much you add of carbon monoxide, you are not going to affect the rate of this reaction. Okay, so the rate of this reaction is affected just by the concentration of NO2. Also, another point, really important point here is that we can see here that there is a coefficient of 2 in the concentration of NO2. This coefficient is not related with the stoichiometry of the overall reaction. Okay, so these numbers, the orders of each of the reactant in a rate law, you can't determine those orders, those coefficients, by looking at the stoichiometry in the overall reaction. You can determine this, as we mentioned before, by doing those experiments where we change the concentration of one of the reactant and we keep the other one constant, and we look to the rate and see if there is some change. And if there is some change, then we can determine the coefficient of that specific reactant. Okay, so this coefficient we can determine by looking at the stoichiometry in the overall reaction. Okay, so those 2 points are really, really important. Now let's say that this mechanism, the initial step is the one that is slow. Okay, so the first step of this reaction is the one that is slow. That means that um, in this case, remember that I mentioned before that for the rate determining step, that elementary step will dictate the rate of the reaction. Okay, so if the elementary step in this case is the initial step, that initial step is the one that is going to dictate the rate of the reaction. So that means that this coefficient basically is are the stoichiometry of that rate determining step. And in that rate determining step, the only reactant that we have is NO2. But because we have a coefficient of 2, that will means that we have 2 NO2 in the first step. Okay, so the first step, we know this because we established that the initial step is the rate determinant step, and because the rate determinant step is the one that is going to establish the rate law, and we knew before that the rate law here, that means that this reactant is going to be the reactant of that first step because it's the step of the rate determining step. Okay, and we have 2NO2 because we have a coefficient of 2 in the rate law. Okay, so now we have the reactant of that first step. Okay, um, so it will be good now to make the product of that first step of the mechanism, and we have NO2 and NO2. Let's bring the overall reaction here to see which one can we produce. We need to produce one of these two products because we need to keep, this is the reaction. So we are creating a series of steps to explain how can we obtain the NO and how can we obtain the CO2. So in this first step, we can't produce the CO2 because we don't have carbon. So the only molecule that we can produce is the NO by this step, or these two molecules. So how can you think we can create NO by combining these two compounds? There you go. One of this could give one oxygen to the other one, and this will become NO, and the other one will be NO3. So those are the products for our first step, or the initial step, okay, NO plus NO3. So here we have a step that explains how NO was made. But what happened with NO3? NO3 is not part of the overall reaction. Okay, NO3 is not part of the overall reaction, so we need to consume that NO3 in the next step. So sometimes we're going to produce some compounds that are not part of the overall reaction, and we need to consume them in the next step. Those type of compounds that we produce but then we consume in a mechanism, they are known as intermediates. Okay, so because NO3 is not part of that overall reaction, is an intermediate. So we're going to use that in the next step, and we are going to combine the NO3 with the CO, the other reactant that we have in the overall reaction. And maybe now by combining these two compounds, we can produce the CO2. So how can you think we can produce the CO2? NO3 will give one of his oxygens to CO, and we will have CO2 plus NO2. And that will be our products of our second step. So now we have explained how the CO2 is produced and also how the NO is produced. Now let's highlight some important points of this mechanism. Since the first step is the slowest step, it gives the rate law, okay, that was established in the beginning of this problem. Now, if you add up all of the individual steps, in this case, the two steps that we create, we get the stoichiometry, or we also get the overall reaction. Each step balance, and because that this is a plausible reaction. So let's see that in the view of the example that we have working. So we have here the overall reaction, our step number one, the first step, that in this case was the rate limiting step, and our second step. So what happened if we add both steps? Okay, as we mentioned before, the intermediate, in this case the NO3, they are produced in this step and consumed in this reaction, so they cancel because they are not part of the reaction. And do we have another reactant in one step that is a product on the other one, on the other step? Yes, we have here one NO2 and we have here one NO2 and NO2 here, so we may cancel also those. And when we add both equations, we have the NO2 plus CO produce NO plus CO2, and this is our overreaction. So that means that because of this, because we obtain here the same stoichiometry as the overreaction, this this different step, this mechanism, this group of steps is a possible explanation to how to explain how these products are formed in this reaction. Now let's talk about catalyst. The catalysts increase the rate of reaction by decreasing the activation energy of a reaction. The catalyst changes the mechanism by which the process occurs. Here we can see the reaction progress of a reaction. We have here on our left our reactants, here on the right the products, and the red line is the reaction progress of a reaction without a catalytic. And the blue one is a catalyzed reaction. So first of all, we can see that the catalyst doesn't affect the energy of the reactant, nor also or neither the energy of the products, but it will affect the activation energy. Here, from here, this point to this point is the activation energy of the reaction. And as we can see here, the catalyzed reaction decreased that energy, activation energy. Remember that the activation energy is the minimum energy required by a reaction to form the products. We have three types of catalysts. The first one is homogeneous, heterogeneous, and the enzymes. The homogeneous catalyst, in this type of catalyst, the reactants and the catalysts are in the same phase. Many times, reactants and catalysts are dissolved in the same solvent, as we can see here in this example. Both of them are in the same phase as liquid. And heterogeneous catalyst is in different phase than the reactant. So often gases are passed over a solid catalyst. The absorption of the reactant is often the rate determined instead. So here we have hydrogen and carbon, and they basically are molecules again in the gas phase, and this is the solid is the catalyst. They are absorbed by that catalyst, and then the reaction can take play in that surface. So this type of catalyst just provide the environment where this reaction can take place. And the enzymes are biological catalysts. They have a region where the reactant attach, and that region is called the active site. The reactants are referred to as substrate. So here we have basically a model where we have an enzyme, we have the substrate, the substrate binds to that enzyme, and then we observe the products that will be formed by that reaction catalyzed by the enzyme. So we'll finish our model number 14 of chemical kinetics with this topic of the catalyst.